Let's talk about directional derivative, which is key to understanding gradient descent. And gradient descent is itself a very powerful tool to update weights and parameters in machine learning. Fine. So, how is directional derivative defined? First of all, let's consider function z is equal to f of xy. This is a two variable function. And if we plot this function, we will get a surface. So let's say this is x, y, and z here, and any arbitrary surface is there, like this, any arbitrary surface, and so this is a surface of any given function. And let's consider a point P in xy plane whose position vector r vector is defined by its coordinate xy. So we say r vector is equal to x I cap plus y j cap. And let's say I want to move an elementary displacement in this direction. In this direction I want to move in any given direction whose unit vector is defined by n cap. So n cap is basically is in the direction of pq vector. So here I have this q and whose coordinate is x plus dx comma y plus dy. So we have this pq vector, which is the dr vector, is equal to dx I cap plus dy j cap. And so if we consider z corresponding to p, which is this height, and corresponding to q will be, let's say, this height. So if we see how much change we encountered in z if we moved from p to q, so this will be the elementary change in z, which is dz. So directional derivative is defined as the elementary change in z while moving from p to q, which is the elementary displacement over this elementary displacement, that is pq. If we say mod of this pq vector is dl, so we say dz over dl is directional derivative. This is how we define directional derivative. Directional derivative means it has we are moving in certain direction, that's why it's directional, and derivative is basically slope here, dz over dl. Now let's establish an important relation between directional derivative and one of the quantities known as gradient vector. So dz while moving from p to q can be thought of as two-step process. First, move in the direction of q and then move in the direction of in x direction. So if I say this point is r, so dz is equal to change in z encountered while moving from p to r plus dz while moving from r to q. This is total dz while moving from p to q. This is a two-step process. And by the way, we can write this dz from p to q as del z over del y, because we are moving in y direction keeping x constant, and by the way z at xy times dy plus dz from r to q is del z over del x, because we are moving in x direction keeping y constant, and by the way g is at point r, whose coordinate is x comma y plus dy, and this times dy. And this quantity is approximately equal to del z xy, because if you are taking partial derivative at r or at p, both will remain same with respect to x, because this pr distance is very small, this because this is elementary displacement dy, and this is equal to del z over del x times dx. By the way, oh oops, this is also x. So this we can write dz is equal to del z over del x times dx plus del z over del y times dy. This is really an important equation in multivariate calculus, and we have proved this. This is important because we will be encountering this kind of thing in our deep learning also. Fine. So here, if we define a new quantity that is your gradient vector, and this gradient vector at point P is equal to del z over del x I cap plus del z over del y j cap. This is your gradient vector. Why this gradient vector? Because you are basically calculating partial derivatives at p. So del z over del x, del z over del y. This is gradient vector. So gradient of whose? Gradient of z. And at what point? At point P indicated by this position vector. And I'm putting an arrow sign here to indicate that this is a vector. This is how we symbolize the gradient vector. This is the definition of gradient vector. And we have this dr vector as dxi cap plus dyj cap. So this quantity can also be written as del z over del x I cap plus del z over del y j cap, and this with the dot product of pq vector or dr vector, that is dx I cap plus dy j cap, using this relation because we know how to express the dot product of two vectors in its components. So we can say that this quantity is our gradient vector, that is del z at r vector dot dxi plus dyj is nothing but dr vector, and this is dz. And so if we divide dr vector by its magnitude, that is dl, then we will be getting dz over dl is equal to I'm writing here del z dot dr over dl. And by the way, what is this dr vector upon dl? This will be a unit vector, a vector divided by its magnitude. So we can say this is also equal to del z, the gradient vector, dot n cap. N cap is our unit vector along dr vector. And this is nothing but dz by dl is the directional derivative. This is the relation between the directional derivative and this gradient vector. That's it.